Morning, everybody. Welcome back. Good job being here the day after the exam. I have finished the first pass. I'm most of the way done with the second pass, which is so I grade the right, just is it right, is it wrong, just going through. And then I go back and I check to make sure that the correct answers are like truly correct, right? That you've shown work. And then what I'll do is I will post those today. It'll be today that I post those grades. So look out for that. And what's the caveat? What's the special? What's the asterisk on your grade that gets posted today? It's what? It includes as if you did the autopsy, right? So you need to do the autopsy to get the grade that I'm giving you today, right? If you don't do the autopsy, then you don't get that grade, your grade goes down. The step that I am not going to be doing is to go back and check the wrong answers to see if you were doing it right, but maybe made a math mistake or that kind of thing. So you're going to show that to me during the test autopsy, okay? That's me partly being lazy and me partly having to do the Physics 4A exams as well. So. After the autopsy grade. So let's say that you get the only number I can remember is 6. Let's say you get a 6 out of 12, right? The raw score would be a 50%. I'm not putting that one in. I'm putting in the 70% that comes off of my scale, right? Just so you know, so it's not like you don't go in and see your raw percentage and go, right? All right. When you get your score, after I post it, when I get your score, and you need to talk to me, I'm not available tomorrow. I'm giving tests all day tomorrow on 4A. But Friday would be a fantastic day. Come into grass. If you want to talk about your grade, you're worried about things, whatever, okay? I can try and make myself available via Zoom if coming to campus is too hard. I can try to, we can set up something maybe while I'm in that room, I can pop up Zoom or something. But please feel free to come and talk to me, whatever your concerns are. All right. That's right. We get to start magnetism. Hey. I've already warned you about this section, right? This is the hard one. Mr. Bailey, you really need to stop saying stuff like that because it's all been hard, and you're not wrong. You're not wrong. It's all hard. Okay, but here's the thing with magnets. Do I want those? No, I want. No. Here we go. I have here a couple of magnets, okay? Obviously, different colors mean something, right? It's just so fun, right? I mean, who doesn't like it when a magnet, right? It's like magic. I love it. Going back, magnetism was discovered, if I want to use that term very loosely, way before electricity was. Electricity, of course, the phenomenon of lightning is ancient and it's more ancient than us human beings. The phenomenon of discharge and static electricity has been observed throughout the ages, but in terms of our understanding and really scientifically trying to nail down what's going on, that really starts in the 1700s for electricity. Magnetism goes back to ancient times in terms of its utility, in terms of attempts at trying to understand what was going on. The story goes, and I don't know how historically factual this is, but the idea surrounding it certainly is. There was a shepherd out walking on the islands of Greece, and back in the day they had these sticks to keep the sheep in line, the shepherd's crooks, they're walking sticks, right, to either defend the flock or push the sheep around. And they would cap the ends of the sticks with metal, iron, to just kind of protect it, right? Their walking stick want to protect it. And they noticed, one of the shepherds noticed that certain kinds of rocks would stick to the metal that was on the ends of the staff, right? You put it down on the ground and these flecks of rock would come up. And so he took that to the village, high leaders, whatever, mucky mucks, and said, hey, look, this is a pretty interesting thing. And supposedly the story goes that the shepherd's name was Magnus. And so they called the rock magnetite. And that's where we get our word magnet today, right? So take that idea, right, and now start playing with these rocks that seem to have this force that pulls them together, and then put them near metals, and then the metals become magnetic. And if you can take a piece of metal and let it suspend freely from a string maybe, or on a piece of cork floating in water, all of a sudden that piece of metal will turn and twist itself around and point in one direction. No matter where you go, you can turn yourself around, but that piece of metal is going to orient itself. What was just invented? Compass. We've been using magnetic fields much longer than we've been using electric fields. The story of electricity and magnetism really begins with magnetism. We teach it out of order because magnets are harder to understand, okay? Because there's a lot of stuff, okay, that's going on when it comes to magnets. And I just want to demonstrate some of the, amazing things that magnets can do. So what I've got here is I've got a magnet. This is on the Elmo thing here, the overhead projector, right? And I've got a magnet that's sitting in one of these bases, okay? And it's a support where the base can freely spin, right? So essentially what have I got here? I've got a magnet on a freely rotating, it's a compass, right? And it's very similar to, say, what this is, right? Here's a compass. This one just happens to have some numbers on it, okay? So that we can orient ourselves. Now, which way do compasses point? I mean, it's got a preference, doesn't it? They usually point north. Okay? Why? Oh, North Pole? Santa Claus? Okay, let's just make sure that we are calibrated correctly. Santa Claus lives at the? Penguins live at the? We're good? Right? Okay. There are some penguins at the Galapagos Islands. They don't count. They got lost. Okay? But no penguins at the North Pole, but yes, penguins at the South Pole. No Santa Claus at the South Pole. They've been bad this year. Santa Claus only lives at the North. We got it? Okay. So, this compass, this magnet, oriented itself in something. There was a force that got applied to this magnet, right? See how I try to knock it out of position and it goes back to where it was, okay? So there's a force that exists that is causing that magnet to get pushed in a certain direction. Where is that force coming from? The earth? So gravity? What Where's the force? What do we call a pattern of forces that exists around an object? A field. So the Earth has a magnetic field? More on that in a bit. Does that magnet have a magnetic field? Yes. Does this magnet have a magnetic field? Yes. In other words, a pattern of forces that exists around it. Okay? So now, I'm going to override the Earth's magnetic field. I'm going to come in here with this magnet, and I'm going to push and play, right? And we can see here that the red end of my bar magnet and the green end of my compass, they don't like each other, do they? Do you see how it pushes it away? Right? But what about the red and the red? They like each other, don't they? Okay? So there's a field. There's forces. Guess what we get to do? Right? We got to find out where it's coming from. We got to be able to explain the field. Got to know what the field looks like. All that kind of stuff. What direction's that way? North, right? So okay. So New York is that way, ish, right? Japan somewhere over there, right? Bay Area, then Japan. Hawaii's more that way, right? Okay, and then Los Angeles is like somewhere that direction. Okay, we're all oriented in space and kind of know where we're going because you're about to get lost. Okay. What end of the magnet do we call this? Of the compass, rather. Or ask it a different way. What direction is this? North. So this is the north end of the compass, right? The north end of the compass points towards the North Pole. Is everybody with me? Okay. Hold that thought. Because if I take this magnet, right, and I go with the red end again, right? What do you know about the poles of a magnet as far as like what attracts and what repels? Ooh, okay. So let's back up. What flavors? What are the flavors of a magnetic field? North and south. So it's not positive and negative the way we had with electric fields, right? It's north and south. So is that just a different name for the same thing? No. More on that in a bit. Okay? So we talk about north and south poles. And we know when two north poles try to get together or two south poles try to get together, right? We know that they repel each other, don't they? Okay? When you have opposite poles, they will attract each other. So how do we tell which is which? Like I know the green and the red are repelling here, right? Okay? So I know one of them has to be a north pole, north pole, and one of them has to be a south pole. And I know that these two are attracting each other, so I know they have to be opposite. But again, I don't know which is which. So how do we determine which one's north and which one's south? And how did we decide? It's not Ben Franklin's fault this time. Which way is that? North. This is the north end of this magnet. This one's labeled. North end because it points towards the Where does Santa Claus live? At the North geographic pole? But what magnetic pole has to be that way? If that's the north end of a magnet, by definition, it's pointing towards what pole? A south magnetic pole. You've been lied to. Santa Claus is real. But you've been lied to about where he lives. It's not Alaska. Santa Claus lives at the North geographic pole, right? Alaska, Yukon Territories, Canada, parts of Russia, all that, the ocean that's at the top of the world, right? We call that the North Pole, but that's the geographic North Pole. The magnetic South Pole is also up there. By the way, those two places are not the same place. The Earth's magnetic poles are shifted away from the Earth's geographic poles. The geographic poles are defined by the axis on which the Earth rotates. That axis is tilted at about 23 degrees from the vertical, which is the reason we have seasons, okay, is that axial tilt. But we define the axis around which we spin as the rotation axis of Earth, North Pole in the northern hemisphere, South Pole in the southern hemisphere. The Earth's magnetic field poles, though, are reversed from the geographic poles for the reason I just told you. The north end of this magnet is pointing which way? North. It's pointing north. This is not my fault, okay? I'm just trying to clear the record. It's pointing north. That direction is north, but in order for that direction to be north, the pole that's out there somewhere has to be a what? South magnetic pole. So the Earth's magnetic poles are reversed from its geographic poles. The Earth's south magnetic pole is in Canada somewhere. It actually moves around quite a bit, miles over the course of a year. Okay? The Earth's north magnetic pole, located where geographically? At the South Pole, is actually not anywhere on Antarctica. It's in the middle of like the Atlantic Ocean somewhere. Okay? So the poles, the north and south poles, are offset from their geographic poles. And if you look on an actual physical map, not Google Maps because it doesn't tell you anymore, you can see that there is a difference between, they'll print on the map what the magnetic correction is for true north versus magnetic north. Magnetic north is what you hold as a compass. True north would be where the actual North Pole is. And where you are on the surface of the Earth changes the angle between true north and magnetic north. And you thought navigation was easy. I'm trying to decide if I want to tell you the next part. The poles have flipped their orientations in the past. On average, every 750,000 years, 750 to a million years, somewhere in there, the Earth's poles flip. North becomes south, and south becomes north. It takes about 1,000 years for that pole reversal to take place. But there is in the geologic record evidence that north and south could have been flipping as much as twice per day during these pole reversals. It takes about 1,000 years for it to settle down, but while it's undergoing a reversal, it can be fluctuating quite a bit. As a matter of fact, right now we have a dipole field for the Earth's magnetic field. That's the simplest magnetic field you can have. But you can have quadrupole and octopolar magnetic fields. where there's basically multiple north and south poles pointing everywhere. How do we know all of this? Well, how do we know anything about deep time or deep history? Geology is always the answer, okay? So there's a kind of rock. We call it magnetite nowadays, but these are iron-bearing rocks, iron being a material that's very susceptible to magnetism. There are ferrous metals, it's iron and cobalt and nickel, sort of right there in the middle of the periodic table, that are very susceptible to magnetic fields. They'll orient themselves in a magnetic field. We're actually going to talk about this. I'm gonna tell you exactly how the sausage is made here. We're talking about bar magnets right now, but very quickly we're going to leave bar magnets behind, and I'm going to very elegantly sweep them under the rug, and you can't see those anymore. And then we're going to learn all about magnetic fields, and we're only going to learn about bar magnets at the very end of our magnetic field section. It's because bar magnets are hard, okay? But for the time being, right, let's just say iron likes magnetic fields. And when you heat up iron-bearing materials, they get to a temperature called the Curie temperature, above which they cannot have a magnetic field. They can't respond to a magnetic field. And so if you take iron and you heat it up and then cool it down in the presence of a magnetic field, all the iron atoms will align themselves in that magnetic field, and then they're frozen that way. Lava is above the Curie temperature when it comes to the surface of the Earth. And as it solidifies, the iron in it will match its orientation to whatever the magnetic field that's around it. Since most volcanoes don't happen near industrial grade magnets and happen near the Earth's magnetic field, geologic lava flows and other rock formations store a magnetic record of what direction was north and south throughout time. And this is one of the ways that scientists discovered plate tectonics. Plate tectonics wasn't known about until the 1960s. It was hypothesized around turn of the century, 1900s, but the scientific evidence was not found until we went and tried to find the Russians in the Atlantic Ocean during the Cold War. We were looking for Russians. What we found was plate tectonics, okay? They were dragging magnets all over the Atlantic Ocean looking for submarines, and what they found was that the sea floor had magnetic stripes on it. Personally, I think it was just a big hard drive, but that's just me. So knowing that the poles of the Earth reverse themselves, and knowing that they reverse themselves every 750,000 years or so, and it's been about 1 million years since our last reversal, guess what's happening? It looks like we're in the beginnings of a reversal. We can thank the British Navy for the information here. The British Navy kept accurate records starting in the 1820s all the way up until now about where North Pole is. Okay? You can measure the deviation in magnetic declination between true north and magnetic north, and the sailing ships from starting in 1820 kept accurate records, and they're stored at the Naval Archives. So you can go back and find the location of the North Pole, and so we've been able to track for the last 200 years the location of the North and South Poles, and they've been moving, and the rate at which they've been moving has been increasing over time, which is, again, indicative of what we found in the geologic record. So we're due for a flip. It's going to be interesting when it happens. The good news is that we don't navigate with compasses anymore. I mean, some Boy and Girl Scouts might still do that, right? But what do we navigate with now? Right? GPS doesn't care about what the Earth's magnetic field is doing. Okay? So GPS cares about relativity, which is a physics 4C topic. It doesn't care about magnetism. And so the fallback, though, I mean, when GPS fails, you navigate via compasses. And when compasses fail, what do you navigate by? The stars. From a period, I think it was in the early 2000s till the mid-2010s, U.S. Navy personnel were no longer required to learn navigation by the stars. Starting in 2017, I think it was, the Navy reinstituted navigation by the stars as a class that all naval cadets have to take. Why? Because GPS jamming is really easy now. So, yeah, we're going back to the stars. All right. What does all this have to do with the problem? Besides Santa Claus being at the wrong pole? Okay, so here I've got a magnet, okay? And you'll notice as I orient this magnet in space, the other one will respond to it, okay? I'm applying a force, right? I mean, obviously there's forces being applied here. But what is the force causing? Not just movement, rotation. What do you call a force that causes things to rotate? A torque. Somebody said moment. That's the engineering word because they don't want to deal with torques. They call it something else. It's just a torque, right? There's a torque. You thought this class couldn't get any worse, right? And now I've mentioned the T word. All right. Let's sum up what we know. Come on, iPad, you can do it. Okay, magnetic field. North and south poles. We know that. So if I draw a magnet, screen's not on? Of course it isn't. Easy to fix. Maybe. There it is. Thank you. So take a bar magnet. I'll give it a north and a south pole. Rule number one for magnets. You never ever have a north pole by itself. And you never ever have a south pole by itself. The magnetic field is always a dipole field. A dipole is just a fancy word that means plus and minus together, or in this case, north and south together. The words in physics that we use for this is that there are no magnetic monopoles. So a monopole, we've studied monopoles in this class. A positive charge is a monopole. It's a one-signed thing. Okay? Magnets and magnetic fields always have a north and a south pole. And it doesn't matter if I cut this magnet in half. What do I get? I get two magnets, okay? And if I cut those in half, I get four magnets, both north and south. How far can I cut before I run out of north and south poles? The answer is I can go all the way down to the electron. Because an electron has a north and a south pole. In other words, like charge being a fundamental aspect of our physical universe. So what have we got so far? We've got mass, we've got charge, now we have magnetism. All the way down to the smallest building blocks, we have magnetic fields, north and south poles. Okay? So mass, charge, and now magnetism are intrinsic features of our universe and the material that makes up our universe. Light being the outside exception, but you'll study that in Physics 4C. Okay, so that being the case, what does the field look like? Well, back when we did electric fields, we kind of had some rules for like where electric fields started and where they ended and what was going on. Okay, we have similar rules for magnetic fields. by choice, so as a definition or a way for everybody to talk to each other, magnetic fields, well, they don't start and they don't stop. Magnetic fields only form closed loops. What does that mean? We need some directionality associated with this, but you can really only go around a circle kind of two ways, right? Clockwise and counterclockwise sort of idea. So we decided, we, not us, old white guys, decided that magnetic fields would come out of north poles and go into south poles. What does that mean? It means that when I go and I draw my field, okay, I can start drawing it anywhere on this circle, this loop, but I'm going to say it comes out of a north pole. So give it a direction. And it will loop around and come into a south pole. And this is where a lot of textbooks and animations and visualizations on the internet and all that kind of stuff, this is kind of where they'll stop, implying here that, again, a magnetic field line like has a beginning and has an end, but it doesn't. It forms a closed loop. That loop continues on through the material itself. For clarity, the lines on the insides of the magnets are often not drawn. But what you need to realize is that the magnetic field is fundamentally different from an electric field, because electric fields start and stop. They begin on positive, they end on negative, right? They have a definite beginning and an end. Magnetic fields don't have a beginning, they don't have an ending, they form a closed loop, closing on itself. It's just that the directionality of that is such that it comes out of a north and into a south. So we're sort of externally looking at the magnetic fields, external to the magnet. We're not worried about sort of what's going on inside, just with the acknowledgement that you have a continuous field line. So if we take two magnets like this, okay, you'll see this, and I'll draw this quite often this way. And so this is, again, we're sort of cheating a little bit here, and I'm already telling you exceptions to the rules, which is bad. But where do the magnetic fields come out of? South pole, right? Oh, North pole, right? They come out of the North pole, and they go into a South pole, right? So what direction does the field between those two magnets point on the screen? To the left or to the right? It points to the left. And here you can see I've only drawn the field lines between the poles of these two magnets. In reality, I should be drawing the whole loop, right? The whole, oh boy, that went wrong. Okay? But for clarity, we often don't draw the whole loop. So it's a bit of a, yes, we know they form closed loops. They're fundamentally different from an electric field, which has a start and a stop. However, we often only want to know a magnetic field within a region of space, right? We sometimes usually are like, well, what's going on right here, okay? In which case, we're not so much worried about what the entire field is doing. We're just looking at a small portion of it. So I would apologize for that, but that's just, I don't know, kind of the way it is. Okay. And this is where I start sweeping things under the rug. Oh, and by the way, I should say that we can draw field lines that also go off to infinity. So where do those two loop around and close on themselves? Back here, right? So yes, the closed loop, but if I wanted to be very clear, I would make sure that those lines would go through the magnet themselves. How many field lines could I draw? An infinite number, right? So similar to electric fields, we don't draw them all. We draw enough to represent sort of the strength of the magnet. If one magnet has twice the number of field lines as another magnet, we assume it's twice as strong. The lines cannot cross or tangle, just like electric fields. So they won't cross over each other. They won't intersect. They'll try to bend out of each other's way. Which is why when two north poles try to come together, what happens? This field line is trying to come out, right? Those are all trying to go out, aren't they? Well, they can't touch each other. That's not allowed. So what do they have to do instead? They'll deflect away from each other, right? And those fields won't want to come together. When I come over here to my compass with my magnet and it moves away, I'm literally trying to bunch up magnetic field lines together in a space where they're not allowed to cross or tangle, so it'll move out of the way.
What happens to the vectors when you force them together?
Yeah, we haven't gotten there yet. Yes, you're going to wish you hadn't asked that question. Okay. I'm starting off really slow because this is going to get bad pretty fast. Okay. Let's start. Well, okay, this is where I sweep things under the rug. And we're going to start, all of a sudden, it's going to sound different. But I want to strike out for territory that is familiar. So the familiar territory is electric fields and charges inside of electric fields. We defined the electric field as that pattern of forces that exists around all charges. We're going to do the same thing. We're going to try and define the magnetic field as the pattern of forces that exists around all magnets. It's just testing that with other magnets gets really hard, so let's test it with charges instead. So like before, where we had an electric field, right? We had a, say, positive charge, and we knew the field lines are doing this thing, and we put a test charge in here, right? We said, okay, well, we know the force is going to be away, right? Two positive things are going to be away. And if I go over here, okay, it's going to be away. And if I get closer, it's going to be a bit, right? We can wander around with that test charge and try and figure out what the forces are doing and maybe what this pattern looks like. We're going to do the same thing with magnets, and we're going to do it with a charge, which I know sounds kind of weird, right? Like, we're talking about magnets, Mr. Bale, just use a magnet. Well, turns out it's easier to do it with a charge. Because one of the, again, sort of key differences is that the magnetic force, by the way, symbol B for magnetic fields. In physics, we don't use the symbol M for magnetic field. That's been, mass took that one, okay? So we use the symbol B, capital B for magnetic field. So the magnetic force isn't equal to, because we'll get to equal to in a second, it's proportional to the amount of charge we have, which kind of makes sense, right? The force that something feels in an electric field, does it depend on the amount of charge? Like, think of Coulomb's law. Does the amount of charge matter? If you have more charge, what happens to the force? It's bigger, right? Okay. So hopefully it kind of makes sense that a magnetic field and a charge, the more charge you have, the greater this effect's going to be. So it turns out that those are directly proportional to each other. But, and here's the big caveat or the big difference, that charge has to be moving. Charges experience no force from a magnetic field if they're standing still. The only way that a charge will experience a force from the magnetic field is if it is moving. How did we discover that? Well, can anybody tell me what a moving charge is? It's a current. Good job, right? charges going along a wire, right? They're moving down the wire. We first discovered this force from magnetic fields by studying circuits. Wires, when current was flowing through them, would deflect compass needles. The wires themselves were making magnetic fields. We're going to get there, okay? But the flip side of that is that an external magnetic field, say from a bar magnet, would affect the current that was flowing in the wire. This was the thing that got Michael Faraday started down the path of discovery. It wasn't discovered by him. Another guy named Ørsted discovered the connection between currents and compasses. But when Michael Faraday saw this, he couldn't unsee it. Like it just captivated his imagination, and he needed to understand what was going on. And even better is that was there a way for him to capture the motion of the compass? Was there a way for him to push compass needles around and capture that somehow and turn it into work? Which is why he would be the first person to invent the electric motor. Proportional to charge and velocity. All right. But if the velocity is parallel to the magnetic field, this force was 0. So in other words, if your magnetic field and the particle's velocity was pointed in the same direction, or 180 degrees, you ended up with no force on this charge. It's undeflected. Its path is just a straight line. But if the velocity and magnetic field were perpendicular to each other, the magnetic force would be the most or maximum that it could ever be. I should say also that the force is proportional to the strength of the magnetic. So increase the amount of charge, force go up. Increase the velocity, force go up. Increase the magnetic field, force go up. But direction matters. We need these things to be anti-parallel to each other. Now, charge. Scalar, vector, or elephant? Charge is a scalar. It's like mass, right? Now, it has plus and negative versions, but that's not a vector direction, right? We don't need to know. Charge doesn't have a direction. It doesn't matter what direction charge is in order to know what the charge is. Velocity. Vector, scalar, or elephant? It's a vector, isn't it? It's not speed, it's velocity. And velocity very definitely depends on direction. Magnetic field. It's a vector. You guys know where this is going, right? Because it also turns out that it's proportional to the sine of the angle between the velocity and the magnetic field. What are we talking about here? We're multiplying two things that are vectors, and we're getting another vector out, right? Because force is a vector, velocity is a vector, magnetic field's a vector, and what's the only way we can multiply vectors together and get another vector? Cross product. And what do we know about the output of that cross product? It's mutually perpendicular to the vectors that went into it. Huh? It means that the magnetic force on a charge is the charge times the cross product of the velocity and the magnetic field. And the direction of that force will be perpendicular to both the velocity, and the magnetic field. How many dimensions are required in order for three vectors to be perpendicular to each other? I can do two vectors all day long. Those two vectors are perpendicular to each other, aren't they? Right? So are those, right? But now I need a third vector that's perpendicular to both of those. We have to go into the third dimension. There's no way out. Up to this point in this class, we've cheated. Now, are electric fields three-dimensional? Yes. Have we always drawn them two-dimensionally? Yes. Can we do that anymore? No. We have to work in 3 dimensions. How good is your programming skill? How good are you at MATLAB or mathematics? Do you see the problem? Like, how do you do this on a screen, on a 2-dimensional screen, right? Okay. How do you do this on a whiteboard? How do you do this on let's go old school, piece of paper? Let's punt that. Let's come back. Let's come back and see what we figured out so far, if anything. Okay? We'll get to the 3D mess in a second. This is a big day for you. You're learning stuff about Santa Claus and penguins and 3 dimensions. Yikes. All right. All right. So, magnetic force on a charged particle. I've already dropped this on you. Okay. Let's talk about that force. Let's talk about units. Let's get all this done here. All right. What are the units of force? Newtons. What are the units of charge? Coulombs. What are the units of V? Meters per second. What are the units of magnetic field? Whatever it needs to be to get this thing to come out in newtons, right? Is the answer. Okay? Because we're multiplying stuff together. The units of the magnetic field is a newton divided by a coulomb times a meter per second, which is really awkward to say. And so we've renamed it to the Tesla. After Nikolai Tesla, an American immigrant, Croatian American immigrant, inventor of the late 1800s, early 1900s-ish time period, named the unit, the SI unit for magnetic field in his honor. More on him later when we get to AC circuits. What's that?
Did you just say Tesla?
Tesla, T-E-S-L-A.
Your shorthand?
Yeah, just capital T. Yeah, okay. We use T for Tesla. Now, there's another way to go about talking, because what's a coulomb per second? It's an amp, isn't it? So this is a newton per amp second. Okay. If you haven't given up on units yet, now's the time. Okay? Just use SI units for everything. If you're given a distance, do it in meters. If you're giving a time, do it in seconds. If you're given a charge, do it in coulombs. If you do that, and you're solving for a force, what are you guaranteed to get? Newtons. If you put SI units in for everything, you'll get the SI unit for the thing you're looking for out. the relationships, the equations have the dimensional analysis baked in so that you don't have to do the heavy lifting when it comes to the units. So you can continue trying to figure out these compound units, or you can just kind of believe. Sometimes belief is easier. Okay. That's a Newton per amp meter, not an amp second. Because I can do units too. Okay. There is another unit that rears its head every once in a while, and that's the Gauss. Wonder where we got that one? The Gauss is, well, I did that the wrong way. 1 Tesla is equal to 10,000 Gauss. That's 10 to the 4. Okay. The reason that Gausses exist is because the Earth's magnetic field is pretty weak on the Tesla scale. The Earth's magnetic field is down to around 1/10,000th of a Tesla. And so quite often in physical sciences like geology, geography, that kind of thing, some chemistry where they're using small magnetic fields, they'll choose to measure the magnetic field in Gauss rather than anything else. Again, because it's, I don't know, easier. I don't know. I think it just confuses people. Just stick with Tesla. All right. So that's the units. That's the force. I'll talk about it right now. How do you find a cross product? Ask your calculator. Or like, there's kind of two ways, aren't there? There's the matrix, and then you put in your. That's supposed to be a z. That was supposed to be an x. If you need help remembering how to do this, come find me. I'll walk you through it, right? But you do the that minus that. And then you cover up the j's, and you do the that minus that with the minus sign in it, and then you and then do that and that, right? And you write it all out, and bloop, falls out. And then there is the one where the cross product between two vectors, its magnitude can be written as a times b times the sine of the angle between them. So both methods we will have to use at various points. Given the choice, physicists will usually use this one. Why? Less work. Physicists are lazy, right? We'll always do the thing that makes less work for ourselves, okay? But what that does is it just gives us the magnitude of that cross product. It doesn't give us direction. So now we have to deal with direction and how we figure out what that direction is. And this is where we are going to start the insanity that is 2.5 right-hand rules that you are going to be learning this semester. Now, you may or may not have, let's see, did Dr. Kerfoot teach you right-hand rules in Physics 4a? You did, for torque? Yeah, I wonder why we're having to use it again, right? Okay. So which one did he teach you? Because there's several that all do the same thing. It's just a different, how do you hold your hand? Was it like this? No?
You point your fingers to
Okay, so he did the fingers with the thumb like this, and then you bend your fingers?
Yeah.
That's the one? Yeah. Okay. This and this are the same thing. Okay? So I can help you with both, but let's stick with the one that Dr. Griffith did most of all. I like to call that the handshake right-hand rule, because your hand starts in what shape? The handshake. Okay? It starts fingers straight out, thumb kind of open, right? So you can, right? Okay. It's always awkward to do a handshake nowadays, isn't it? Like, do you shake hands? Right? Okay. So it's the handshake rule. Oh, that was nice. That was nice right there, okay, right? But you're holding your hand. Okay, so what does that mean? I can find the direction of a cross product if I point my fingers in the direction of the first vector and then bend my fingers in the direction of the second vector, whatever direction that happens to be, and then my thumb ends up being what? The direction of the third vector. What we're trying to do here with our hand is get three directions that are perpendicular to each other, okay? So I've got the sort of plane in my hand, and then I've got my fingers bending, which gives me two perpendicular directions, and then here's my third with my thumb. If you want to hold your fingers like this, it's basically the same thing, right? Where you've got one finger pointing, another one perpendicular, and then your thumb points up. It doesn't matter, okay? So why are we talking about that here? Well, it's that mutually perpendicular thing again. So let's just say, for the sake of argument, we have a speed. A charge is moving at some speed v across the screen from left to right. And then it's in a magnetic field that points up. To get the magnitude of this force, we know it's going to be q times v cross b with all of its vector glory. But the magnitude of this will be q times v times b times the sine of the angle between them. Well, what's the angle between these two vectors as I've drawn them? It's 90 degrees, right? So what's sine of 90? It's 1, isn't it? Which is why you'll often see the magnetic force written as QVB. If it's ever written QVB, we automatically know that everything's perpendicular to everything else, because basically sine of 90 went into that thing. Okay? So what direction, though? What direction is perpendicular to both that velocity and that magnetic field? It's either into or out of the screen, isn't it? I want to be perpendicular to both v pointing to the right and b pointing up. And so which one is it? Is it into or out of the screen? Well, the answer is the right-hand rule. We define this by taking our right hands. Sorry, all you lefties out there. You have an advantage. We'll talk about why in a minute. What's the first vector? It's v. So you start with the first vector. You shake your hand in the direction of v. So this would be holding my fingers pointing to the right of my right hand. Okay? And then you want to bend your fingers in the direction of the magnetic field. What do you have to do with your handshake to do that? We have these things called wrists. They're really fancy. Okay? You rotate so that your fingers can now point up. If you're causing yourself physical pain while doing the right-hand rule, you're doing it wrong. I can't do that. Mental and emotional trauma, perfectly fine. Physical pain, we're doing it wrong. Okay? So you shake, you rotate your hand so that your fingers can naturally bend in the direction of the magnetic field, and then the thumb tells you the direction of the cross product, in this case, the force on this particle. What direction is it pointing? Out of the screen. Well, how do I draw that? And I've practiced that one. Like, How bad can an isometric drawing be? Bad is the answer. Like, does B and V, do they look like they're at 90 degrees to each other? No, because it's an isometric projection. It's all blah, okay? So no. The answer is no. We don't do it that way. Instead, what we're going to do is we're going to adopt a system, okay, that is in use in every book and pretty much every website. I mean, sometimes you get a website that's got a nice three-dimensional applet or something on it, but it's decidedly old school and it decidedly works. What's that? Looks like an X, doesn't it? It's not. What's that? Looks like a period or a dot, doesn't it? It's not. That's how you draw a vector going into or out of the page. Why X and why dot? Sometimes you'll see circles drawn around these. For clarity, I don't think it makes it very clear. Okay? What is a vector? Like in our imagination, I know it's something that has magnitude and direction, but like in our imagination, what is it? It's an arrow, isn't it? Okay? And if I take my bow and arrow and I aim my vector at you, what do you see? You see the tip, the dot coming straight at you. But if you're the one firing the bow and you let go, what do you see? You see the feathers, the tail heading away from you. So every time you see an X, which way is that vector going? Away from you, into the screen, right? And if you see the dot, duck. It's coming towards you, right? Out of the page. So now, when we go and we say, okay, we have a V and we have a B, just like we had before, right? Those two are in the plane of the page, nice and easy. But can I now indicate the direction of the force? Yeah, I might draw it off to the side a little bit, but I would say the force, whoops, is wrong. Which way is it? It's out of the page. V, B, which way is my thumb pointing? Out, away from the page. This works on the screen. It works on your iPad. It works if your piece of paper is flat on the ground, right? Okay? Whatever that it's always out or away from the page. Okay, so what happens if we have our V this way, but our B goes down now? Everybody do the right-hand rule for that one. I shake in the direction of V, right? And then I've got to rotate my hand so that my fingers can point down at 90 degrees. And my thumb is now pointed which way? Into the screen. So how would I indicate the force there? It'd be an X. All right. If I have a uniform magnetic field, uniform in that it's the same everywhere in this region of space, even though I haven't really drawn it that way, right? And I have a particle, a charge, moving at speed v upwards. Find the direction of the force on this charged particle. Okay, so what do we start with? Which way do we shake with our hands to start with? What do we always lead with? The velocity, right? It's QV cross B, so you do the velocity first. So our hands shake upwards. All right, now which way is this magnetic field pointing? It looks like it's all pointing in, right? Because all those X's. So my fingers would then bend into the screen, and my thumb is left pointing which way? To the left, right? Yes, no? Shake in V, fingers bend into the screen, thumb is left, pointing to the left. How much practice do you need in this? All of it, right? So you need to like quiz each other. You need to make up a bunch of flashcards. You need to do something, right? I think there's a couple websites that will do this, but they'll just come up with variations of these problems where you just practice doing the right-hand rule. You're going to want to practice it. You need to be able to do it forwards and backwards. What do I mean by that? Here is a velocity, okay? And the force on the particle is this way. What direction is the magnetic field? Well, I know that my V has to be down, right? And I know that my force has to be to the right. So that only leaves my fingers being able to bend which way? Into the screen. So the magnetic field here would be into. So we can do it out of order. We can do it in order. What's the magnitude of this number going to be? QVB. But the direction will be given by the right-hand rule. I'm out of time for today, but I do have to explain how this circles back, what the path of these particles is going to be, and why being left-handed is an advantage. But we'll do that next. Question?
So I'm noticing that for, let's say that the force is like the second example to the down. It's going to be out of the page or into the page, right? Is that the same for, and it seems to be the same for the positive, if there's a positive. Would it only be out of the page when it's in negative and positive?
Yes, but do the right-hand rule for that. Try not to think of it in terms of positive and negative.
That makes sense.
I will see you on Monday.